Taking a look at the arc in problem number 40, it looks plain as anything that we're going to have to do this in polar form. We're going to be working with ds, still r d theta, since we're still working with a piece of wire. And over here, all the wire is out at a radius of r, and theta varies from 45 degrees to 135 degrees. The difference is that for a change, we're not given r, we're given L. That ought not to be too much of a problem. After all, L, the length of that piece, is simply a fraction of the circumference. In this case, it's pi over 2 times r. We need r at any point. That's going to be 2L over pi. Now, we ought to be in fairly good shape to set up our linear mass density, m over L, also our very useful dm ds. Our center of mass calculation is, as ever was, 1 over m y dm, which in this case is going to be 1 over m. Ooh, polar form. Let's convert y into r sine theta. And dm, we said, was lambda ds. That gives us lambda. Check. R is constant? Yes, R is constant. R over m. Integral of sine theta r d theta. Don't forget that other r. That other r is going to move out to the front here. And we'll get lambda r squared over m. Let's see whose derivative is sine. Oh, that's right, it's negative cosine. Evaluate that from 3 pi over 4 to pi over 4. Plug in for lambda. The m's will cancel out. You'll be left with r squared over L times your evaluation of negative cosine theta from 3 pi over 4 back to pi over 4. Pause and finish the problem. If you get 4 rad 2, having canceled out 2 of your 2's, over pi squared times that total arc length, you'll be in the right place.